Hello, everybody. My name is Sayan Bhattacharya, and you're watching the Digital Mind Melt. In today's episode, you will have Gopi Vijay Krishna, who is the science director at the Foundation for Cultural Renewal. He's also a researcher at the RSRS in Salt Lake City, US. This episode is special because of several reasons. Firstly, we are going to dive deep into the fundamentals of electromagnetic theory, but mostly our scope lies in atomic structure. I can definitely see talking to Gopi in several different episodes, probing him into more fundamental questions and seeing how he answers in a very interesting kind of a way, where he explains all these scientific theories but without a model. And he also talks about the limitations of models. I hope you enjoy this episode.
We are not taught any of this. We are not taught that things come within boundaries and then you can do certain things in this boundary. Science has been disturbed in its development because of other influences which are coming from outside of science. Even semiconductors, if you study semiconductor theory, as I had to, full of contradictions. It's probably a trauma on your mind. And voting has no place in science. If Faraday had to be voted on, God forbid, we would not even have had his theories today. We would not have been able to handle any of it. This is the mind breaker.
Yeah.
This is the fundamental obstacle to learning calculus for students the world over. You have 0 times infinity giving you a finite number. It throws you. You have
So, welcome to the Digital Mind Melt. And you are very interesting in several different ways, right? The first time, basically, I come to get out of your podcast in the Demystify Sci was to kind of illustrate stuff without models. And that was something that really hooked me into it. Like, I mean, how does that work exactly? Uh,
yeah,
because the whole system has, I don't know, brainwashed me or also put into my head that we need models.
yeah.
Uh, it's just impossible without them, without those stories to kind of come. And then when we come to the details of the stories, there's a lot of stuff missing. So,
Yeah, yeah, yeah. Very true.
uh,
So, yeah, please, tell me which aspect you'd like me to explore on this, and I will dive right in.
yes, I've made a few notes, so maybe I
Sure.
will do a bit here and there. Yes.
Yeah, yeah, yeah.
So, you have spoken about the dangers of projecting our own technological metaphors onto nature, right? That for the
Yeah.
idea of projection itself,
Yes.
and like factories, telegraphs, computers, right? So, if you could design a new metaphor for how we should approach nature today, what would that be? How might this metaphor help us break out of disciplinary silos, right? So, if you could riff on that a little bit.
Yeah, sure, of course. So, um, one of the main causes of this way of looking at the world and trying to, fit what we already know onto the world is, it's not nice to say it, but it's actually a kind of mental laziness. Because what happens is we tend to become very familiar with something. We get into grips with it. And then our love for that thing is so strong, and our comfort in those concepts is so strong that we just carry it over. And we say, okay, now let me look at the world this way. And what happens there is, repeatedly you spend enormous amounts of time where your mental pictures clash with the thing that you're trying to study. And you have to basically grate away at it over decades. And it's an insanely inefficient and impractical way of doing things, but we all do it. So that's the cause of it. Like, if at least closer to the root cause is we just become so used to something, and that psychological factor is left out of reckoning in most scientific descriptions. Nobody speaks about how lazy or not your mental thought process is going to be, or how much you like something. So that's why we end up doing that. And in terms of metaphor, actually, metaphor is drawn from language.
Yes.
And language is actually a very good way in itself to speak about this. For example, if I am speaking to somebody in China, or I am speaking to somebody in Iceland whose language is so different from anything that we can talk about with Indo-European, now you have to learn that language.
Right.
It is not enough for you to find words in your language that kind of match that language and try to squish, the two together and try to make sense of it that way. No, you have to learn that language. And that requires more effort, that requires more patience, that requires being willing
Training.
to wait for all the mutually consistent connections to form in this new language. That is what we need. So it's the same thing when you talk about physics. When you just look at something, everybody loves billiard balls. It's the most easily understandable thing. You can play with it, you can live it. And then we go into the world which is through the microscope, and we just throw that over there.
Right.
And then we don't wait to create a self-consistent picture of the micro world. We don't wait to learn that language. We like our language, we are going to use that over there. So that's what I would say is a better metaphor is metaphor itself, to use language as such as a theme to exploring different areas.
Right, right, right. I mean, on that tangent, I would like to kind of probe you in one particular way with my own personal experience, how I studied and
Yeah,
how I learned about stuff, right?
yeah,
Because it was extremely haphazard. Like things came a lot early, some of the very interesting stuff, and with no explanation at all.
yeah,
And in the later stuff, I mean, I see that, whoa, wait a second, it's so hard to solve linear problems, you know.
yeah, yeah,
That's the realization. So I'll take a very specific example, let's say. So when at the 11th standard, right, like when we kind of come up with physics, right? So
yeah, yeah,
mechanics comes
yeah,
into the picture first, right? So after units and dimensions. So uh, the first thing is that you're into a world where there's no friction. There are boxes, like box-like things, which obeys certain kind of things in that world,
yeah,
right? And there are pulleys which obeys some kind of laws. There are
yeah,
strings which, if attached to strings, they also follow some laws.
yeah,
Then we come to a different kind of scale, which is
yeah,
a very small kind of a scale. All right, where we kind of come to understand what is a wave. And there's a central thing called the nucleus, and then there are things that are encircling it for
yeah,
very specific reason, of course,
yeah, yeah,
which is what quantum, the basic entry point of quantum.
yeah,
So the fact that language itself is pointing to some other language,
yeah,
like one word points to another word and points to another word.
yeah.
So, how would you essentially make this curation process of physics better?
So, for example, when you have the original experiments that lead to a certain idea, then that experiment carries a lot of value to check out a different idea. So, for example, let us say that picture you just gave. Yes, in mechanics, you have things and you push and pull, and you have the laws of the lever, the pulley, and the inclined plane. You get to grips with something there. When you shift from there to the circling things, electrons circling around the nucleus, that whole picture.
Exactly.
Uh, it doesn't hold together that easily. You're forced to imagine it without getting to grips with it. For simple example, if you look at the original writings in the textbook and so on, when Bohr originally created that picture, and he was asked, wait a minute, whenever there is an acceleration of electricity, usually there is a radiation.
Right.
And radiation means energy is lost, and there is no way the electron can be in a circle. It cannot be sitting in one circle because it is going to lose energy because it's accelerating as a circular motion is. So he just said essentially, well, it doesn't do that. Why? By fear. It just doesn't do that. Now, when you think of these things, it creates a mental block in your thought process, because now it's a very different picture than what you had when you asked your physics professor, how does this thing roll down the inclined plane? He will tell you this is how it does, and you put this here, and if instead of a sphere you have a body with angular features, you need to do this and you need to do that. You can hold on to the thoughts all the way. Here it's like a diktat from the church when you say no, it just doesn't do it. Now, what that does is if you have a conceptual fabric, it just creates a jam in that fabric and you can't move. You don't know where to go. And that is the place where you can curate. Like, wait a minute,
Yeah.
what are we actually observing? What we observed is when alpha radiation, I will not even say alpha particles, alpha radiation from radioactivity penetrated materials, reflection was very little, penetration was maximum. So that's one clear thing, that for alpha radiation, this is true. Secondly, we have the thing that in spectroscopy, we see lines. And those lines have a certain mathematical relationship. There is a rhythm to that, and they behave in a certain way. Everything else is what we impose. So we these are the two new words that physics has told us. Now we have to create a sentence out of it. We cannot impose. Like in Hindi they say kalpana. We cannot put our kalpana on top of it. We have to wait to see, okay, so there is a line that is happening. There is also the penetration that is happening. How do all these things go together? When we see electricity being generated out of material substance, was the electricity inside it, or was it something that came about in the process of the interaction? That's another question for logically curating your idea. The usual way of doing it is, oh, you know what?
Could you please go into the rabbit hole of that question a little bit?
Yeah. So, for example, if I just rub my hands together, right, and I generate heat. Now, from that, we normally will not conclude that the hand is made up of heat.
Of course.
Right? It is not an automatic thought. But in this case, what happened is with electrical situation, when they realized that from all different kinds of materials, electron beams are capable of being generated, then the next assumption was, oh, okay, then electrons should be inside it.
Mm-hmm.
And that is a logical jump that doesn't have full support. You cannot immediately say that electron was inside it. All you can say is you did X and therefore Y electron beam came out. For the next one, you have to create some independent other method to figure out whether or not electron, as you think of electron, is actually inside where you think it is. And this comes out very clearly, for example, in nuclear physics, because in certain nuclear deterioration, you have beta radiation coming out, which people have found is same as electron, but with a lot more energy. Now, If that's the case, then we should have electrons circling around the nucleus too, by the same logic. The same logic that we use to put electrons in the atom, that same logic we should use for putting electrons in the nucleus. But we do not. You see, it's because there are all sorts of problems. How does the charge set? And we assume it is charged. So now the charge shouldn't, collapse into each other. Every other place you put a positive and negative charge, boom, they're done. But in the atom, miraculously, they are sitting away from each other, even though they are 10 to the power minus some 15 meters close by. So these are like, they go into full blown fantasies at this point, because now your mind is being stretched to think of things which are not in your experience, but you are kind of holding it because you don't have any other option and you can't think about it. So that's how that rabbit hole goes. Like each, you look at electron, you look at nucleus, you have all these ideas, but it's not necessarily as clear cut as you think they are. And it has so many internal contradictions because we are imposing our language.
Right, right, right. Are you familiar with Rupert Sheldrake's morphic resonance idea?
Yes, to some extent. Yeah, I've read his
Right.
criticisms of modern science and so on and so forth. Yeah.
Yeah, so I wanted to ask you a little bit over there. Like, there's one aspect where he mentions that the fundamental constants essentially they change with measurement, which is very strange.
Yeah.
And this is not with any fuzzy language that the act of observation changes. No, no, no. These are the fundamental constants we're talking about,
Yeah.
like G and
Yeah.
all those constants. So, is this what is your take on that? Like, how?
I think it's, again, when we want a constant, we normally want a solid foundation, because once again we are using the building analogy. We want a strong foundation on top of which we build our whole physics structure, and the foundations are now shaking. You see, oh, the constant is no longer a constant. Everybody panic. And that, it's not a fault of the reality. It's our adherence to the building analogy that has thrown that stuff off. If you look at what you see as a constant, all you can say is it's a relationship. Every constant comes out of a relationship. When you think of say, how when they first figured out the charge to mass ratio and the charge itself and then the mass and everything, everywhere there were actually in the physics experiments, there is, okay, this quantity and this quantity, you take a ratio of those two quantities that you're dealing with, and out of that ratio being a constant gives you a constant, right? That it's a constant ratio. Now, when you think of it as a constant ratio, the ratio gains predominance and the constant becomes less required. So what you're now looking at is, in physical laws, there are ratios that can move and morph. Maybe some move and morph with a time scale of, a couple of centuries. Some might move and morph with a much, much larger time scale. But you are open to the idea that this is a ratio, and therefore, just like you can tune up or tune down something, it is possible for the constants to morph with time.
Right, right, right. Um, so can we get back a little bit into the electromagnetism part? Like, I mean,
Yeah,
to understand the relationship between electricity and magnetism, I mean, without any model at all. And what would the process of understanding look like that essentially? Like, I mean, a very Faraday-like mindset,
yeah,
essentially,
yeah.
right? I have to wear my blue blockers. It's gonna look a little strange.
Yes.
Yeah. I'm very sensitive to blue light.
Yes, 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 yes. So, yeah, the Faraday-like mindset actually is very healthy
Yeah.
for studying of electricity and magnetism. In fact, I would say the Maxwell equations, as accurately as they have been put, in a way also blocked our conceptual development the way Faraday had set out to do. because we froze our concepts immediately into the equations instead of, it's a new landscape. The guy has just spent a lifetime as a pioneer of a new landscape. Let us explore that landscape some more and then come to some ideas rather than just, okay, we have the equation, let's run with it. So that's the initial foray into that. The next step is how to deal with electricity and magnetism on their own terms. Here, I think one of the things that has been done is we have not been able to look at magnetism without thinking of electricity. So this is an assumption that
Yeah.
has been put into our minds. So, for example, when we first, did that wire and we curled that wire and we saw a magnetic field inside it, we did not pause to think, wait a minute, is that magnetism like a way the electricity is, coordinated to produce that magnetism, or is that magnetism as such? It's the difference, like when you, like I said earlier, you're heating, you're rubbing your hand and generating heat versus lighting a candle. Now the candle has that heat as part of its interior process continuously, whereas here you're just incidentally creating it. So we had to think like that regarding magnetism. Is magnetism something that is working in and of itself, or is it only, generated when electricity is made to go in a certain way?
So it's
So
emergent phenomenon, essentially.
yeah. So when you think of it like that, because see, everything is connected to everything else in nature.
Yeah.
Now, if you stop making these distinctions, then everything will become just electricity. That is what has been done. All of physics has been made into electricity. That is, like, we have become monotheistic almost to the whole thing. What is heat? Heat is electromagnetic. What is magnetism? It is electricity in a circuit. What is light? Same thing. What is whichever way you go, you will end up with that as far as the macroscopic thing is concerned. If I push a table, the table pushes back. Okay, what causes that? Electromagnetism. You see, everywhere we go in the usual world, the answer of physics is electricity only. And that, I think, is because, once again, of lack of distinctions in the processes, because magnetism can exist by itself without electricity. And this is very clear in case of our, like a magnetizing a needle or the permanent magnets. All the permanent magnets live there without necessarily having any electrical analog, but we impose it. We try to make it about electrons and orbitals and unpaired electron and blah blah blah. We kind of impose it, but the physics doesn't show us that. With nothing, you don't get hit by a electric shock when you touch a magnet. Nor can you drive out electricity from that magnetic substance directly. It doesn't work like that. So I have actually written an article about electricity and magnetism and how to distinguish between those two, and especially in terms of dimensions. Because if you study carefully everything that electricity is doing in terms of its activities, you will see that it has a predominantly one-dimensional quality.
What do you mean by dimension over here?
Dimension, just in terms of, like, say, x-axis, y-axis,
Like a
z-axis. So normally, when you think of a solid object, our imagination is always, embedded within the three-dimensionality of something. When you start thinking of these realities, which electricity and magnetism open up for us, the reason they are strange is because they are one-dimensional and two-dimensional realities. They don't exist in three dimensions. So that's one of the reasons they are kind of like it, but they're not really like it. They have this kind of ghostly existence as far as our own perception is concerned, but a very real existence if you think of them in terms of a different dimensionality and a world of a different dimensionality. So electricity, for instance, always short circuits in a line. We fill it with wires, and it's almost always something that goes along a line. That's its natural state. And when you create those, Lichtenberg figures and everything, you can see the lightning all crackling away like a linear, jagged sword. And so everywhere when you see electricity in action, it is always expressing itself in one dimension. Whereas when magnetism, it is always two planar figures coming together. And you will see that in multiple ways. You will see it in the fact that even the two poles of the magnet are always together because it's a two-dimensional process. It's not a one-dimensional process like it is the case of electricity, where you can have one beginning, one end, and those beginnings and ends can be in different spots. So that is what we normally call positive and negative electricity. That's the polarity of electricity. So you can link to that. I don't need to go into too much detail, but that's the way to learn its language.
Immediately, yeah. Like it immediately brings to the question, right? Like, I mean, again, one more word that has been overused, but without a formal definition, which is a particle.
Yeah.
There's no definition properly. Everyone
No.
writes some of their own stuff, and
Yeah.
that's how I've seen it.
Yeah.
And I mean, the particle basically, I mean, can we treat them as balls, like cricket balls or tennis balls, right? And that's the analogy that we kind of essentially always think of, even when the quantum physics is being taught. Like the classical like mindset first appears, and then
Yeah.
we talk about the strangeness in the phenomenon.
Yeah.
And I would also like to basically understand about the observation part. But before that, like if I talk a little more on the atomic structure aspect, right? What are your how would you communicate about the void essentially? Like if we pack a lot of atoms together, right? There are void and they have their own set of geometries, right? And I mean, I saw some content from I saw it in a very open-minded way, which is from Terrence Howard. I don't know if you are familiar with his work.
The recent interview that he gave with Joe Rogan, right?
Right.
And even with Demystify, he gave the talk. Yeah. Yeah. Yeah.
Yes,
Go
yes,
ahead.
yes. Like what I like about his approach is that like he is actually targeting a question, and don't fully like completely I agree on the utility of it because I'm not very familiar with the stuff that he's talking about, but he definitely has some interesting arguments.
Yeah.
And, but I would really like to understand this first thing. What is this ether, right? And then suddenly this whole thing went away, and nobody talks about it, right? And
Talks about what?
ether.
Ether. Yeah. 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 Yeah.
Right. Like, I mean, waves, right? Like, I mean, the sun is traveling 8 minutes to Earth, right? Like, what's happening there exactly? Like, can you please zoom into that phenomenon a little bit better? Like,
Yeah. So to start with what you first started with in terms of the particle, and even the wave which comes about in quantum mechanics, here you see the prime examples of the kind of deadlock and logjam that takes place when you transpose everyday ideas straight away into the macroscopic realm. Where are we getting the particle idea? Like you said, it's the tennis ball, it's the cricket ball, it's that. So it's solid, right? It's a solid conception. And solid, by definition, are in all three dimensions static. So that's our notion. It's a self-contained three-dimensional, reality.
yes.
Waves, on the other hand, they are kind of free in. You could say it's kind of free in a dimension. It's not entirely solid because the liquid as such always has a mobile element, and it's not the same thing. But it is also part of our macroscopic experience.
Yes.
Solids and liquids, these two states of matter, form our mental pictures of things that are happening in the quantum realm. And so now we throw it in. Now, how do we throw it in? We make it very small. It's the oldest trick in the book. You take something and you make it very small. So now it's so small that you can't see it, but it's still there as you thought it is going to be in the microscopic realm. And here you see that it is possible. This is just my understanding so far. It is possible that our way of understanding one-dimensional realities has been to take a three-dimensional reality and just squeeze it down to a very small level. So then all that is left is like a streak. If you take a cannonball, then it's an entire area of space that it occupies, right? It's an entire volume. But if you take only a very, very, very tiny electron, as they say, then it only leaves a one-dimensional streak behind it. And that one-dimensionality is what we are seeking. But we are still stuck with this relic. So now the only compromise is to make it a tiny bomb. So once you understand this like inner struggle in concept making of scientists, then you see, oh, what is actually there? And like in the sense of what is the right concept and what we are doing in kind of this weird compromise between what we experience and what we don't. So that is the particles story, you know. Then you come to the wave story. What is a wave story? Wave story is that there is a back and forth. Now, back and forth that happens in case of a pond is the up and down in position of water with respect to air. It can also be in other case, like if I take if I take a phone or if something and then I scratch it on a rough surface, right? Initially it vibrates a bit and then it goes smooth. And that's one of the things in mechanics. Initially the friction is a little bit more active, and then as you overcome friction, it goes to the kinetic friction, things go a little smoother. So even in terms of physical forces, you see that little bit back and forth that happens before movement sets in. So as a concept, we don't have to automatically think of wave. We can think of back and forth of some kind. There is a movement and there is a resistance to that movement. Whether that movement is in one dimension, whether it is in two dimensions, whether it is in three dimensions, that's another story that we have to examine. But you recognize there is an activity and then there is an opposition to the activity that comes about. And when the two are tussling with each other, you have the wave. And when one overcomes the other, then you have whatever it is. Where in case of electron, they say, oh, that's its particle nature being expressed. In terms of other radiation, you'll say, oh, it's a particle nature being expressed. But where you catch it in the tussle, they say, oh, it's wave behavior being expressed. So this is what we are doing. We are looking at what is actually happening, and now we are looking at the behavior, and we are putting things into that. Now, the right here is your ether question.
Yes.
Exactly here is your ether question, because when we think of a pond and we throw a rock into a pond, we have the pond, we have the water, we have the air. So we already have certain prerequisites, like we have the two states of matter, air and liquid and gas, and there is an alternation that happens in between. So whenever we think of a back and forth, we are now transposing a material into it, because we are unable to think of a back and forth without this, model aid, without the aid of this model. So there is both the rightness and the wrongness of the ether idea coming in. The rightness of the ether idea is that, yes, there is another level of reality in which this activity is happening. And that level of reality, whatever you call it, has its own laws. And you can technically call it, say, the electrical ether, because it's the electricity acting in its own domain. That you can call it the ether. But that's very different from this, again, mental laziness inspired transposition of a liquid into the world.
I mean, we also say it in our normal conversations, right? Like phone is out of juice.
Yeah.
I mean, juice. Again, the thing, it's liquid, it's just somehow, but it's not nothing like that. It's completely
Yeah,
different.
exactly. Exactly.
Right, right,
So
right.
that's the ether thing. It's not right. It's not right and wrong just like that. It's about how the mind is creating the concept suitable to what is being observed or not. If it is doing it correctly in harmony with what is being observed, then it is a right use. If it is a transposition, imposition, projection, what have you, then it automatically becomes the wrong use. And it was good to get rid of that part, but it was not, we threw the baby out with the bathwater, is what I think.
Right, 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 right. So I guess we were basically speaking about the ether, right?
Yeah. Yeah.
And how we essentially project our own experiences of solid, liquid, and gas into that kind of a, and we treat it like that essentially.
Yeah.
And and you are saying that that doesn't work. That
No.
metaphor doesn't work. You have to think with a different kind of a mindset, right? But
Yeah.
also very difficult because we are not seeing such stuff in the classical world. Uh,
Correct.
so
Correct. Yeah.
uh,
Yeah.
yes, yes.
But it's also trying to be fair to the reality too. If reality asks us to learn a different language, we got to be willing to put in the effort to learn it. And that's what it is. In the that's what it is at the end of it. Yeah.
So can we say that this is more aligned with the computational model, essentially, that everything is computation, and then
Um.
uh, you're allowed to make different stories by different kind of.
In some respect, but in one place where you inevitably have to approximate is the geometry of, say, the points at infinity and so on and so forth. So, for example, like computation, we don't realize the hardware and how it determines our, you know, the capacity to compute. Even a simplest program to the most complicated program, in terms of display on a screen, for example, it cannot display anything other than four straight lines, which is this one, and those at 45 degrees, because everything is a square pixel. That's the physical structure of what we are dealing with. And that's why the computation cannot display anything other than those. Everywhere else, as soon as a curve is involved, it's an approximation. That's the reality. And same with everything that has to do with the analog constants like pi and so on, and e, and everything that has to do with the transcendental numbers. All of them are only approximations in terms of computation. Like you can take a compass and nicely draw a circle, but the computer as such, unless it is robotified or something, it doesn't do the same thing. And that what that does is it very quickly leads to untenability in our calculations, even when we come from solid to liquid. Because one of the things that people saw, like there was a lot of research in the 70s and so on, where they were trying to see what is possible computationally and what is happening in, say, fluid flow and then turbulent flow and all of these things. And they're going on hitting against this thing that over and over again, you cannot model it or compute it exactly, because you're dealing with irrational numbers. You're dealing with, complex numbers being expressed as irrationals. It's all over the map.
But
So this,
what is the fundamental argument behind the fact that if the approximation kind of works, then I'm equally kind of, I take it seriously, right? Like, for instance, whether free will exists or not, I believe that I have free will
yeah,
because that's basically the mindset that kind of helps me out live effectively, right?
right. That is useful to a certain extent, but then we also have to face the inevitable question, is it true or not? In the sense, something can be useful, but that doesn't necessarily make it true. And the truth of it has a lot more carrying power when you're dealing with things. So for instance, what has happened in case of mathematics is that we have melded once again mathematics and engineering together.
Yes.
So for an engineering mindset, pi can be 3.14 with no problem.
Yeah.
Uh, for a mathematician with the clarity of ideas, if you call pi 3.14 as a rational number, so to speak, it's an atrocity because like entire domains of mathematics simply fall apart if pi was just 3.14. Like entire structures just go away. And so that's the difference. We have the mathematics has its own truth, and we have to be able to follow that truth without kind of short circuiting into the engineering. Like let the engineering be the engineering, and let the mathematical development, the conceptual development, let that be going on its own consistent road. Where the two merge, obviously there will be some give and take, but the circle is still 3.14 all the way to infinity. It's only our practical measurement technique that determines that we stop at 3.14. So it's we have to distinguish those two. And reality as such, it is very possible beyond the point, it is not computable. And we are kind of butting up against it over
So
and over
seemingly you're
again.
saying like it's not possible. Like if we just put in more power, more fuel into the machine, right? Like we will like hit a kind of boundary for computational understanding.
It's a dimensional issue. For example, I'll give you a very simple example. If you have, say, the question of how many planes does it take to make a cube? Yeah. Well, cube is three-dimensional. A plane is two-dimensional. Now, what is our usual mentality? Oh, you know what? Stack them.
Yeah.
Stack an innumerable number of planes. Yeah, and you get a cube. But in reality, you never get to three dimension using two dimension. You have to cheat. You have to introduce a very tiny amount of three dimensionality in our dx or something. We have to cheat somehow, and then once you get that, then you kind of stack it and you get whatever you get. So this is what is happening when we are trying to get to the three dimension using a two dimension. You can put as much power as you want, but you know that in terms of planes, you can get only planes. And to get from plane to cube, you need something else. You need that third dimension. If you have only two dimensions, there is no way in the world you can stack as much with as much power as you want to get to that next level. So it's that kind of a thing. Like we are not taught any of this. We are not taught that things come within boundaries, and then you can do certain things in this boundary. If you want to go beyond that boundary, you have to do something else. No, we think we have one thing and we just force just pound away and we get there. It's a very, once again, uh, mechanical and forceful way of thinking. It may not be true.
Yes, yes, yes. I understand like your perspective absolutely, and where exactly these are issues. Like I want to get into maybe one practical kind of an example so that like we can understand it a little bit more.
Sure.
Like for instance, in integrations, like we take rectangles.
Yeah.
That is the approximation, and we sum the areas of the rectangles, and then we come up with another concept called dx,
Yeah.
which is again a very difficult thing
Yeah.
because it's smaller than the smallest stuff
Yeah.
again.
Yeah.
How has that not treated human well? Like, can we basically get into that territory a
Yeah.
little?
Yeah. Of course. Happily. So there is another example, once again, of the lack of recognition of, say, the requirement for a different dimension. Let me give you an example with a simple triangle, right? Triangle is half base times height. How do you get that? Well, I mean, you can there are various way to do that, but one way is, you take your square and or a rectangle and you say, okay, this is going to be half of this, and depending on how the triangle is squished, you can show that it's the same area. So there is a simple way of doing the area of a triangle using geometry. Why? Because you have two dimensions and you are totally used to two dimensions, absolutely no problem. Now, imagine you had to do that using one dimension. Then what would you do? You will say, okay, I'm going to take a series of lines and they're going to shrink in this way. They're going to have the shrinking capacity. They go from 0 to all the way till the length of the triangle. And then you pause it.
You're again taking two dimensions, right? Because you're taking one for the length and one for the...
Yes, you're doing that. But the way you're doing it is you're starting not with a rectangle and a two-dimensional and chopping it up. You're starting with a line. So here you're trying to do something that is, in that sense, a jump. You're going from a line to the area of a planar figure, right? You're going from a line to an area of a planar figure. So because you're doing this dimensional gymnastic, you are forced to introduce a 0 and an infinity together. What is the 0? The 0 is the area of your line. What is the infinity? The number of your lines. So 0 times infinity giving you a positive number at the end of it. You see, this is the mind breaker.
Yeah.
This is the fundamental obstacle to learning calculus for students the world over. You have 0 times infinity giving you a finite number. It throws you. You have no way of getting there. There's no way to get here from there, So, but if you understand that, okay, you know what? Maybe what this is a proxy for, the 0 infinity business is a proxy. It works, but it is a proxy for the two-dimensionality of your triangle. So if you start with something that is of a lower dimension than what your object really is, then you are forced to put in the 0 and infinity and figure out rules to come up with it. If you do not start with lines to figure out planes, and you start actually with planar figures to figure out planes, then it's a two-step process. Take your rectangle, chop it in the right way, and you get your area of a triangle. So the mentality, this is what I was trying to talk about. It can go from one to the other. You can do the exact same thing with the volume. You can do the exact same thing. You can take a square, like a pyramid. You want to create a volume of a pyramid. You can take a square and go tuck, 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 tuck. And then you can sum all of that and you get, 1/3 the area times height and things like that of a volume of a pyramid. Or you can also take an entire cube and from one vertex, you can create different pyramids. And when you do that, it's pretty straightforward. You can go look it up. When you do that, you create 3 pyramids out of one vertex of that cube. And therefore, it is a cube over 3. So that's your volume of a pyramid. There you are comparing volumes to volumes, areas to areas, lengths to lengths. That comes with a certain self-consistent power that you can explore. What calculus is trying to do? It's trying to do the bridging. It's going from 1 to 2, 2 to 3. And in doing that, you're caught in this never-never land of 0 and infinity. You somehow just forget about it, jump over it. Understand the rules. Don't think too much about 0. Don't think too much about infinity. Just get your formula and move on. But so that's what we do.
Right. I mean, oh yeah. I mean, it's
Yeah,
like
it kind of blows your mind. Like once you
it
think of it.
definitely kind of blows your mind. Right. I mean, it's really, really interesting. And I was actually wondering in my head that if there is something which is very much visible to the human being in a day-to-day kind of activities, to an average human being or
Yeah.
animals, right? Like where they could basically come up with an idea of dimensions which are, let's say, other higher than four, right?
Yeah.
And make those projections into this world.
Yeah.
And could you come up with such an example where our intuition kind of works in that kind of fashion, or any
You're
exceptional?
thinking of going into a little bit higher dimension and then still.
And that becomes important or necessary for whatever reason. Because here's the thing, right? Like we have to come back to culture and technology, because that's what gives us meaning, right?
Yeah.
The
Yeah.
mind essentially is
Yeah.
watching the whole thing at the end of the day, if we be very
Yeah.
practical, right?
Yeah.
And
Yeah.
the reason why we have the computers is because of electricity. That's why we worship electricity, maybe,
Correct. Yeah.
right? Because
Yeah.
the computers
Exactly.
have done a great job at
Yeah.
a lot of
Exactly.
things.
Yeah.
Uh,
Yeah. Yeah.
I'm trying to understand. I mean, even you can go back a few thousand years. That's also totally fine.
Yeah.
Like how else essentially from nature we can take that into consideration way more seriously, and
Mm.
that has promising avenues.
Yeah. I can give you one clear example for this. So, consider the issue of expansion
Okay.
in terms of heating, right? When you heat something, it expands normally, and for most substances. You cool something, it contracts. And something that would have thrown us when we first started looking at this in high school is, you have this story of this plate with a hole in the middle,
Yes.
right? And they ask you, when you heat it up, does the hole, yeah, does the hole become smaller or bigger? And like all kids, we're like, no, the hole becomes smaller because the material expands. And they tell you, no, it's a photographic expansion. It's like zooming in, and the whole thing becomes bigger, and the whole thing becomes smaller. Now, here is something very unique, like an entire increase or decrease in size that has the clear concept that you mentioned before of four dimensionality being projected into the third. For what happens, say, when you take in a regular ordinary sense, if you take a tennis ball or a ping pong ball and you poke it through a paper, right? If you imagine you have a paper and then you are poking a ball into the paper and then you're tearing it and coming out the other side. So if you just think of it like that, initially what do you see on the paper? You see a small circle,
Yes.
then you see a bigger circle,
It's a
then you see a bigger circle,
smaller.
and then you get the maximum size, and then on the other side then it starts decreasing. So you have an expansion out of nothing of a circle in the plane, and then you have the contraction into nothing of that circle into the plane. So there is that aspect, not that entirety of it, but that aspect coming into play when we are heating something. You're actually increasing it while heating and decreasing it while cooling, which, by the way, has no other explanation in terms of our regular three-dimensional stuff. Every explanation that we give for heat fails because we think of atoms and them pushing around, and then you push this way and you push this way and it expands. No, that doesn't work because there are asymmetries in the expansion, which a symmetric system like a ball and spring model can never cut it. I've given a presentation on this actually, on the reason why heat is its own element. We don't normally think of heat as its own element. We always think of it either in terms of electromagnetism, or we think of vibrations of objects or whatever. We always think of it in terms of something else. But that's not really true if you go through the whole span of phenomena that have to do with heat. You will see that no, heat is its own element. It can interact with gas, it can interact with liquid, it can interact with this thing, but it is its own element that has its own properties. And the first step we take into understanding the properties is to realize partially not fully three-dimensional, and it's pushing into the fourth dimension. So that is like a simple thing, something expanding, accessible to everyone, but it is calling upon a concept that is almost drawn from higher geometry, if you will. But it matches, it fits, and it fits much better than all our usual, conjurations of that.
Absolutely, absolutely. I mean, that's very interesting, actually. I mean, this is probably the right place where I kind of like. I mean, I want to explore this, the and difference between these two kind of waves. One is the sound waves, and one is the electromagnetic kind of
Yeah,
waves.
yeah.
Now, there are certain similarities in both of them as well, right? Like, for instance, we have the fundamental and then the harmonics in sound, and which we can completely come out with harmony, Western harmony, with and the music and all that stuff. And on the electromagnetic side, I mean, we also have the hydrogen spectrum, where something similar kind of happens. And so how does a person essentially like grasp this concept in a more abstract way, I would say, so that it makes sense? Because there are also lots of differences between these two, right? So how what is the way with which we can model this up, without for a lack of another word?
Well, yeah. So when you're looking at sound waves and when you're looking at what are usually called electromagnetic, you have, first of all, the dimensional issue that I was speaking of earlier, whereas where the sound is, because it's something that goes through all three dimensions and just spreads, and therefore you have the inverse square law in terms of its intensity and all of these things when it comes to sound, and how it penetrates the substance, whether it penetrates a liquid, it penetrates a piece of metal. You have various ways of coming to it. When you come to electromagnetism, the original Hertz experiment, for example, where he, had that kind of a horseshoe type of thing. And then in one place, you have that electricity spark being generated. And as he went, far away from that apparatus, in his little metal almost ring, because it's not a full ring, it has a gap in the middle, ring with a gap, the spark jumped over. So that is the fundamental phenomenon of electromagnetic radiation. There is a spark being generated somewhere over there, and another metal can then pick up that spark at certain intervals. And when they realized, oh, the spark is easy when it is at this distance and not so easy when it is that distant, that's how they came up with the idea of a wave. Because whenever there is an alternation, up and down, increase, decrease, we think of wave. So then we jump into that and we start describing it. We are not fully sure, and in my opinion, it is not clear whether that wave that we are talking about is actually consisting of alterations in electricity and magnetism, or only magnetism. Because even a magnetic change creates an electrical change, and an electrical change creates a magnetic change. So it is very possible that the wave, which we call electromagnetic wave, has the electro at the ends and the magneto in the middle. So an electric disturbance causing a magnetic alteration, which then disturbs this, that gives out the electrical reaction as a result. So that is a different way of looking at
Also, like
electromagnetism.
yeah, sorry, I was just
Yeah,
there,
yeah,
but
yeah,
I was just questioning about magnetism in general as an
yeah,
idea, just to understand that a little bit better. I mean, one thing I notice is that, of course, that they only exist in solid kind of forms. I never
yeah,
heard of like
yeah,
liquid kind of magnets,
yeah, yeah, yeah,
gaseous magnets. They kind of never
yeah,
heard of such a thing.
yeah.
So what's exactly magnetism? I guess I'm asking, you know?
Yeah. So one way I was trying to describe it in my paper on electricity and magnetism is magnetism seems to be carrying the quality of bulk, uh, and electricity seems to carry the concept of tension. Now, when you take our typical elastic rubber, okay, when you take our elastic rubber, we have both of those together. That's the case with almost all substances that we know. There's a certain amount of elasticity, there is a certain amount of give and take, but in an elastic rubber, it's most transparent. So you can pull stuff. There's a tension, and then there is a bulk. Magnetism seems to be more akin to bulk. Like it increases the bulky nature of something. It is more closer in that sense to solidity. And like you said, you need condensed matter in order to get magnetic activities clearly. You need that. Even oxygen, when they speak about oxygen being paramagnetic and so on, it is best shown in liquid oxygen. You have to cool the oxygen and make it so that it can then come between the ends of a magnet. There you see it. Electricity, on the other hand, is happiest when it can, ionize gas, and it can work very effectively in gas. In fact, the whole what do you call discovery of electricity consisted of its activities in evacuated gas. So electricity and magnetism have this polarity. They don't behave in the same way. Electricity is, you need like gas and you're heating it to a high voltage and everything, and then bam, you have electricity come out by itself. Magnetism, on the other hand, it works in bulk, it works in the cold. So in fact, if you cool things, that's way, way, way more helpful for magnetism, because it works really well. It holds really well when you cool something. Whereas if you heat it, the magnetism is immediately gone. It's very hard to get it back. It doesn't work well with that. Whereas many times you heat something, it actually becomes more electrically conductive. You melt something, you only when you melt it, then the conductivity rises like crazy. So the more the state of matter is dispersed in a way, the better the electricity acts in that. Whereas in magnetism, the more it is put together, the more bulkier it is, the better it acts and better it holds it. So these are just hints. I would like you to take a look at the paper, because there it's the step-by-step development is a little bit better. But we are trying to get to the bulkiness of matter and the tension of matter as if they existed by themselves. And that's why even electricity, what is the first use? High tension cable. Why high tension? Because people originally used the word tension for voltage. Right? Why did they use the word tension? It was not random. They felt it. They felt with all those experiments, they felt it was like a string, and then it breaks. And when it breaks, you have that shock. And that's when you have the dangers of electricity, when that thing breaks. But the tension, they can feel it. They can feel the tension just like you feel a tension in a wire. So we have these kind of half-baked words to express something that is weaving in a different world. And we try to get a hold of it. So, yeah. But at the end of it, once you look at it clearly, you will see matter as we know it, three-dimensional. Electricity is predominantly one-dimensional. Magnetism acts itself in two-dimensional. So it's a 1, 2, and 3 situation. So the three come always together. In your little cycle dynamo, when you have this dynamo, what do you have? You have your cycle pedaling process. So there is movement. And then you have a magnet, which is stationary. And then in that wire, you have electricity generated. So it's like Trimurti. So these three always come together. You have movement, physical movement, electricity, magnetism. These three things will always come together in the 3 dimensions. And that's where you get the left-hand rule, right-hand rule, all those things are coming about, because you're dealing with these different dimensionalities when you're dealing with electromagnetic motors.
Right, 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 right. Like I really like the fact that you kind of switch between kind of two languages. Sometimes you speak like in a poetic kind of a language, right? And you switch back to the physics to explain that.
Yeah.
And it's really quite interesting. I mean, on that particular thread, I mean, I was also going to ask you a little bit about the progress of physics in general. I mean, there has been plenty of criticism in YouTube if I just open it, right?
Yeah. Yeah.
Because apparently for the last 30 to 40 years, like a major breakthrough hasn't happened.
No.
And what's happening in that particular space exactly? I mean, the people have opinions, of course, but I mean, I believe that essentially there are definitely people who have excellent intentions, right, in this world,
Yeah. Yeah.
and who are working very hard, right?
Yeah.
But uh, something's very much missing because all these books are written in the 50s and the
Yeah.
before that
Yeah.
kind of thing. So,
Exactly. I think we kind of took a wrong turn by
yeah.
neglecting this quality of, in fact, the German idealism, if I'm to be really honest. The German idealism was very important because they were builders of thought worlds self consistently. They put a lot of energy to develop thoughts which are all linked to one another and mutually self consistent. And then if you use it, you use it. So what we did was we took a turn, we put utility above consistency. So that has been the case right from like 1870s or something like that. But then the divide grew and grew and grew and grew. And especially after the world wars, the World War One, World War Two, after the wars were done, a lot of science became militarized, and it got itself embedded into the governmental apparatus. Now, this is something that not many people know, but the science as we know it, peer reviewed science, that is a mid 20th century invention.
Okay.
It was not there before that, because what happened was all of the governmental funding to different projects required overseeing, right? You need to check, okay, which project is worth doing, which project is not worth doing. And so that kicked off this whole process of peer review that we know today for publishing a paper. Einstein didn't have to get it peer reviewed by anybody except Planck. Planck looked at it and was like, okay, publish it. And it was the case for many of the previous like stalwarts in science. They did not always have to pass through a democratic process in order to get their ideas through. And what we have done is we have introduced this democratic process. The democratic process is corrosive of science because it's like, okay, does everybody vote yes? And voting has no place in science. If Faraday had to be voted on, God forbid, we would not even have had his theories today. We would not have been able to handle any of it. So that's what has happened. The science has been disturbed in its development because of other influences which are coming from outside of science. Plus, we have not paid enough attention to the consistency of ideas, and we've taken the utilitarian, if it works, do it kind of attitude, which can only go so far. So it is exhausted. Now, that's why all the best ideas come quantum mechanics and before. Like, what? We stopped thinking after quantum mechanics? What happened? Everybody refers back to 1920s as if it's like a knot in history and we have never unraveled it. And we haven't. It's true. We have kind of just kept pushing. Okay, we pushed into nuclear physics, then we got this particle zoo. Then we tried to do a little bit of different dimensional stuff, but it wasn't done right. So you kind of got this wispy string theory out of it, which just kind of dissolved itself into the mist
Yeah.
and nothing to hold. So every frontier, we're not going anywhere. We are running on fumes.
Yes.
That's why. Yeah, that's why there are no new ideas.
Bureaucracy, especially. I
Yeah,
mean, biggest
bureaucracy, yeah,
to science.
money, because technology is a big deal. So manipulating is more important than understanding, right? So money comes if you can make a product. So then That's the whole Bell Labs model, right? The Bell Labs model was a big company which incubates a certain research project, which ultimately gave us the computer, but it doesn't help us understand electricity any better. We are still, even semiconductors, if you study semiconductor theory, as I had to, full of contradictions. There is,
Yeah.
it's probably a trauma on your mind. You don't understand. All you get is, oh, it works, man. The Feynman model. Shut up and calculate. Just go. That's what you get. Yeah.
This is so interesting. I mean, exactly. I mean, this is also something that happened with artificial intelligence. Like some people thought that they would solve in one summer boot camp,
Yeah. Yeah.
and that was just not the case at all.
No.
There was
No.
a big winter, and then suddenly, with this whole feeding of data came into the process, and we came up with these large language models, which are
Correct.
foundation models,
Yeah.
right?
Yeah.
Which
Yeah.
captures a lot of statistics of our activities, of whatever
Correct.
we do as humans.
Yeah.
Very useful. Definitely, I use a lot of that myself, right?
Yeah. Yeah. Yeah.
But I mean, could you please essentially, I mean, comment on this aspect of it? Because I mean, with automations, right? Like, I mean, I automate a lot of my work, so
Right.
definitely that helps me. Uh,
Yeah.
because I believe that for me as a person, I need my time in order to learn about new things,
Yeah.
and that's
Yeah.
very much rewarding to me as a human
Yeah.
being.
Yeah. Yeah.
So, all this noise that's happening of AGI, that about everyone makes a prediction 2030, 33, I don't know. Uh,
Yeah.
let's imagine that we have a particular point where the Kurzweil kind of thinking that we hit a singularity. Uh,
Yeah.
I mean, what are your thoughts on that? I mean, is there any snake oil that is embedded into this story, or is this story completely true? And how does the world emerge out after that?
Out of the whole wave of AI and things like that. Yeah. Um,
I mean,
I
it's not
wrote,
AI, right? Like it started with what you mentioned, that it's all technology driven and money comes with products, which
yeah,
that's the whole thing that's happening. AI came out of that
correct.
economic kind of rise also as well.
Yeah.
Mm.
So I've written this kind of a mini booklet called Technology and the Laws of Thought. It's also up on my website. There, what I was trying to develop was exactly the answer to this question. Well, what is it that we are doing? So technology, when we are looking at it, there are two perspectives to keep in mind. One is the tool perspective, right? You take it, you use it, you get results out of it. Those results are what you want, more or less, maybe 90% of what you want. You can take care of the remaining 10%, and you go ahead with its utility. So that's one road. That's pretty much where everybody is. That's one thing. Little bit people go into the other road where they say, oh, what's the impact of this technology on society? How does it change our way of thinking? How does it change our creativity? How does it change human relationships? And there is a little bit of exploration in that direction, but not a whole lot. Ultimately, people, what they come to is, if you use it responsibly without getting too mad about it, it's okay. But there is a third road which I'd like to emphasize and point out is we are making a kind of a purchase whenever we use a technology. We are basically saying, I am going to, by default, the default setting is this: I'm going to not do something so that the technology can do something. And that's a decision. And in that not doing, there is a repercussion which we have to be very clearly aware of if we are to be handling the technology properly. I'll give you an example. So if you look at the time of the 1830s, for example, right? You mentioned Goethe was living around your time. So if you look at the conversations with Eckermann and so on of his works, you will see that it was very common back in the day that when somebody heard the lecture of some gentleman in some, society, illustrious society or whatever, they would be able to come back and repeat the entire lecture to each other, word for word. Social life of that time consisted in exchanging these entireties with each other. Now, it's a kind of a tragedy that we don't have that capacity to focus and retain anymore. And it's mainly because, again, we've gotten used to letting the technology do things for us, whether it is recording, whether it is, remembering, whether it is what have you. So this is the default setting that concerns me, that we automatically start subtracting our capacities the more we give to the tech. This is the default setting. And unless we recognize that is the default setting, we're always giving an exchange. We are giving over a capacity to get a utility. Until we realize that, we will not be able to take the necessary steps to offset those losses with other capacities that we build ourselves. We have to be able to recognize, okay, we are giving up something by default. So either we cultivate it on our own or we do other things to regenerate that. But until we do that, that technology becomes a liability rather than an asset in terms of our internal development. Like, what is the use of a tech that takes away capacities from us for a utility and leaves us with a net deficit? If it has to be something that we understand, no. It does this, but let me watch out and let me do this so that I can offset the default setting. That has not received as much attention, I would say.
I mean, it's also difficult to understand that because there are a lot of positive sum gains that technology has given us, right?
Yeah.
Yeah,
it has, but it's only the deeper internal capacities that we are dealing with over here in terms of, creativity, in terms of memory, in terms of resilience of thought, in terms of not being very influenced by the outside world and being able to maintain our own, train of thought or train of, life purpose or whatever. These kind of things are deeper inside us. And when they start getting morphed from the back door, we not always catch it. And that's more the thing. It's not about saying, oh, technology bad or technology not to be used or any of those things. No, it's more of, okay, be careful that you don't make the assumption that it is only useful. It's not there is a price and we have to be aware of that price while we use it. Then we can use it without it taking away stuff from us. Like, how many of us would just jump into the car today and somebody tells us an address and just go there without putting it into the GPS, without having to let it, if we create handicaps out of our use of tech, then that requires attention, that requires addressing in some way. Otherwise, imagine what would have happened if we had not started going to the gym with our sedentary lifestyles, right? Or if we had not done our hikes, if we had not done our exercises. What would have happened to us as people if we had not taken those necessary offsets?
They're happening also.
Yeah. Already it is happening. A lot of people, we suffer from terrible health. Now do the same exercise. Imagine the same situation for the invisible stuff, for the memory, for the continuity, for all of these things. If we don't take steps to offset that the way we do with regular exercise for our physical body, if we don't take steps for our mental capacities in the same way, then we allow the wave of AI to kind of submerge us without even realizing. That's coming back to your question. Like, what is the result of this outspurt of all of these different things? What does it actually do? What it's actually saying is, you don't have to think as much. You don't have to think everything all the way through.
Yeah.
A machine will do it for you. Right? And it's taking stuff that people have thought for all these years and taken it all as a database and using that to kind of reproduce and mimic the thoughts and mimic the summaries and mimic all of these decision makings that is otherwise hard for us to do. So it definitely a time saver, definitely in this. But at that same moment, what's the price? The price is we may not be knowing how to think anymore. So that's we won't realize until like we realize after a century that we can no longer remember an entire lecture. We may realize a century down the line that we have a few of us may realize, oh, wait a minute, what about our thinking capacity? Is it going to go the way of the memory, the way of orientation went to GPS, the way, keeping track of our friends went into social media? Is it just going to get sucked away? So that's the default setting that I would caution people about, not about not using something or using something. That's not the issue. The issue is to know the price and to pay the price on our own in a different way. Like we earn it. We earn it rather than just letting it carry us.
It's really difficult because the price is different for different people, because this is I think is it can we calibrate it to humanity in a way that it is just globally we can serve it as one thing, as this is how you kind of trade these things. I mean, we don't have a kind of linguistics to even speak about these kind of things.
Yeah, we don't. That's true. That's very true. Yeah.
And my experience, of course, I'm an engineer. Like, I worked in more applied sciences, so
Right.
the idea, what I felt was the culture is still very Newtonian.
Yeah.
And the idea there is like everyone values some format of real estate.
Yeah.
Either that is the physical real estate they want to capture or some mental real estate they want to capture, right?
Correct.
That's the entire chase. That's the discipline that is being fed back to the system.
Yeah.
Whereas science has already kind of evolved from that kind of worldview. I mean, we know that more advanced kind of metrics like energy and time are probably more special to us
Yeah.
compared to real estate.
Yeah.
Like, we are the only, probably, I don't know, but we are the only species who have invented time. And like, I would like to have a lot of that time to for my own development. And
Of course. Absolutely. Absolutely. And that is again the what it saves us in terms of time. The utilization of the time requires our abilities to match the two. So if we have, say, if you have 2 hours, and how you would use that 2 hours is entirely dependent on how much capacity you are able to bring to those 2 hours. And if you spend it, exploring for science, exploring for this, exploring for that, that's very different than binging on Netflix. You see, there are these choices that we make. There are these choices where the same technology allows for both of them. It gives you 2 hours neutral, but how you use it, it depends on your capacity. And on a large scale, the number of binge watchers might be more than the number of explorers and the number of
Pareto distribution, like, yes.
Exactly. Yeah. So that's the thing. That's why the highlighting of the mental capacity, somebody who values certain things, are willing to put effort, then that's a boon. Then the technology is a definite boon to your life, because you know how to handle that time.
Right. I mean, probably I'm too much of an optimist on this particular thing. Because that's how I see that my life works and functions the best, when I'm in that kind of a paradigm. But I completely understand what you're saying, because it's already happened, all these things. So the health is a very important issue. And I think that in the literature, from what I studied a little bit of health, like, similar things happened as it happened in physics. There has been prioritization of the DNA compared to the mitochondria, which is right now taking up a lot of attention. And and through that process of essentially bringing in bureaucracy into the system and systematizing this entire creative kind of things became static after a while.
Yeah.
And I think we really don't know anything about the human body and the human brain, compared to the advancements we have made in normal non-living technologies.
Yeah. Yeah, yeah. We haven't yet managed to make a leaf.
Mm, mm, mm.
Let's put things in perspective. We have not made a leaf. And we kind of jump and float away on our fantasies of creating consciousness, creating this, creating that, and many other layers of what we think is possible. But right at the very basic level, this going from the non-living to the living,
Yeah.
one leaf. We have not made that jump yet. And we constantly have to calibrate, because then you have the animal capacity, then you have the human capacity. So we have not crossed LKG, not crossed kindergarten in terms of our capacities. We are just only playing in our sandbox where everything is non-living and we can make whatever we want. So our world is a sandbox in that sense.
Exactly. I mean that kind of like, it's a little bit worrying as well. I mean, because like, do you also see that as essentially like what it emerges out of is hubris? That I kind of got something, and that's why the bureaucracy, that's why this is what's happening, and that's why my way of telling the thing is better than yours.
Yeah,
And the hubris, that greed in man of probably coming out of the dominance hierarchy of things,
right.
which we are just humans. Like scientists are also humans, and they
Yeah,
also have dominance hierarchies. So
exactly.
they have to also be under that roles that I am the alpha or
Yeah, yeah. Yeah, yeah, yeah. There's plenty of ego to go around.
yes, yes,
Yeah,
yes,
yeah,
yes. This is extremely interesting. I think that we should definitely catch up this conversation,
yeah,
uh, because I have more avenues now which are a little bit different from this. When in material science, I want to learn more about semiconductors and
yeah.
how this aspect is kind of going. Because I studied electronics in my bachelor's, so I
Right.
did have a healthy dose of quantum physics, but it's nothing compared to a physics student what they kind of go through. Uh,
Yeah, yeah.
but I want to learn about that now. I want to take out some time to get to educate myself into that much depth as much as I can.
Yeah,
And
right. Yeah,
uh,
yeah.
right,
Just a couple of references for our earlier discussion about nuclear and the atomic structure and stuff. There is this wonderful book by Dewey Larson called "Case Against the Nuclear Atom."
right,
And it's a great reference to just open the mind to different kind of thoughts, rather than the well-worn rut that we all have dealing with. And so that tells what actually happens in these experiments and how you can think about it differently and so on and so forth. So that's a good reference. And the other things regarding the technology and the laws of thought and electricity and magnetism, and I've also got a paper on the elements like solid, liquid, and gas, like what do they really mean, and so on. So you might find them of interest, and those are on my website itself. So yeah, you can take a look at all of those areas, and if any of that sparks anything, I'll be happy to jump deeper into all of that.
definitely, definitely. Maybe just the last question before we kind of hang up, and
Sure.
that is, what would be your message to Standard 11 kids? 15-year-old, no, no, 17-year-old, I guess. Yeah.
Yeah.
17, 18-year-old kind of person, like who has so much of energy and enthusiasm and creativity, right? And
Yeah.
because I came out of a factory where I
Yeah.
studied in a place
Kota.
like Kota.
Yes. Yeah. Yeah. Yeah.
Right? So I
Yeah.
kind of know that that's like a grilling kind of a process
Yes.
happening
Yes.
there. You
Yes.
just miss the point after a while. It's like you just have to know how to solve problems,
Yep.
which is also great, but I'm not saying anything bad about it. But like it definitely has its limitations, like into plenty of places where we cannot see things because humans are inherently curious to learn about these how does this work? Because whenever we get into this platonic world, you introduce these new things every day, you know,
Yeah. Yeah. Yeah.
especially in chemistry, like of it every day a new story. Like
Yeah.
I mean, but
Yeah. Very true.
difficult to follow, isn't it?
Yeah.
Mm.
Yeah.
But what would be your general kind of thoughts to curious minds?
I would say not to get swamped by the internet in your thinking. That's number one. And number two would be to be able to pursue something regardless, not regardless, but without putting money at the top, in terms of, being able to pursue something. Because you wouldn't believe how many people have told me that, I would have loved to do research, but we didn't. I love doing that. I still love physics. I still love this. I still love that. But I've not been able to do it because right at the beginning, I decided on this because that would give more money. Now, of course, my heart goes out to them because they have to carry that torch for a long time and not be able to explore it to their heart's content. But it is also possible for those who are at that age to keep that flame alive and take it wherever it, go with it wherever it takes them. Not to make a immediate, compromise just as you enter college, just as you start, looking at the branches of things that will give you a better salary at the end of the gate. And that, I think that mentality crushes a lot more dreams. It crushes a lot more creativity and like real juice of life by doing that at that time. It's okay even if you get lost for a while. It's fine, and then you pursue that without letting the internet kind of lord itself over you. So you have to be open to the idea that there are things in the world that don't exist on the internet, especially in today's generation. They have to get that memo. There's things in this world that have nothing. They won't find a trace of it on the internet, and only that will help you break out of the mental jail and still think new stuff. So that would be my like two key pieces of advice, if you would say, if I'm even in a position to advise. That this is what I would wish to tell.
It's been an absolute pleasure, Gopi. And
Yeah.
I'm really looking forward to our next discussions on various different kind of avenues, because I feel like I'm really talking to someone who is reflecting back some of these ideas which I've always struggled with,
Yeah. I'm very happy. Glad for the opportunity to just speak openly. I don't get that very often. So thank you so much.